All right, so for polar functions, one of the big things that you have to learn how to do for the AP test is figure out how to find the area within a polar curve, okay? Now, the reason why this can be a little bit tricky is not because of the formula. The formula itself is really not that complicated. It's because a polar curve is not graphed in a traditional sense. It's graphed based on an angle measurement, right? And so the curve kind of like builds on itself, and it gets more and more elaborate as you graph it. So you have to pay attention to the angle measurement really closely, and your calculator is going to be kind of your best friend as you go through finding polar areas. Okay, so let me give you a real basic example first. Find the area enclosed by one loop of the four-leaved rose r equals cos of 2 theta. So this is just called a four-leaved rose. On an AP exam, they are probably not going to give you a picture like this, and they're probably not going to tell you the angles that create one leaf like this. So what you would need to do is graph in your graphing calculator, watch it closely. You could even play around with your theta values until you find yourself in a window that, you know, for this case, starts and ends at 0, 0. Or r of 0, sorry. The other thing you could do is you could, when you graph it and you notice the leaves, the kind of corner of the leaf is at the origin, you know that the r is equal to 0 there. So you could find, rather than playing around with the theta values in a calculator, you could find them by hand by looking for when cos of 2 theta is equal to 0. So what you would do is you would say, when is cosine 0? Cosine is 0 at, cosine is 0 at 0. Cosine is also 0, not 0, goodness sake, that's sine. Cosine, let me try again. Cosine is 0 at pi by 2. Cosine is also 0 at 3 pi by 2. And then solve for what theta would then have to be. So pi by 4 is one of your answers. And then you're also getting over here, this would be 3 pi by 4. Now, the way it's listed here is negative pi by 4. Basically, any multiple of pi by 4 is going to work for you. This particular picture is showing negative pi by 4 to pi by 4, just because I'm assuming those are smaller angle measurements and easier, therefore, to work with. Anyway, so you're going to put your A and B values as pi by 4 and negative pi by 4. And then the area formula is 1/2 times r, and r is cos of 2 theta, squared d theta. And then it's really not that different than what we are used to seeing. Now, because polar curves often involve trigonometry, that means that you're going to be dealing with a lot of trig identities, okay? And I believe I've talked to you guys about this before, but it is going to become very important that you remember trig identities. There's a few that kind of come up a lot. The one I'm writing right now is one of those. And you really, really need them in this lesson because you can't integrate sine squared or cosine squared. This is like a mama baby situation. There's really no nice way to do it. So what you have to do is you have to find a way to use substitution with trig identities to essentially get rid of the squared part, because that's the part that makes it hard to find an antiderivative. So for this one, I'm going to use the fact that cosine squared of theta is equal to 1/2 times 1 plus cos of 2 theta. Now, mine is not cosine squared of theta. My problem is cosine squared of 2 theta. So I can modify this trig identity. Basically, I'm just going to double, since this is just a theta and this is 2 theta, I'm going to double the theta amounts to make it fit what we want. So I'm going to do a substitution. And this is going to give me This is going to give me 1/2 times 1 plus cos of 4 theta. Okay, and at this point you are safe to start integrating. I do want to show you one extra little trick. In this question, because the graph is symmetric about the x-axis, and because your intervals are symmetric to one another, what you can do is you can change your interval to 0 to pi by 4, and then you would just double your answer, because it would be basically half of the leaf, and double that to get the full leaf area measurement. So that might be a little bit of a time saver that you could benefit from. I am also going to distribute the 1/2 in the integral. That way I can integrate each thing individually. So we're going to end up with 1/2 theta plus, let's see, 1/2 sine of 4 theta, and then this you have a baby. You have 4 theta is your baby, so you have to divide by the derivative of baby, which would be the same as multiplying by 1/4. And we are evaluating that from 0 to pi by 4. So this would be 1/2 times pi by 4 plus, I'm going to call it 1/8 sine of 4 times pi by 4. And then we got to plug in 0 as well. But if I plug in 0 here, we would get 0. If I plug in 0 here, sine of 0 is also 0. So really I can just focus my attention with this stuff. So I have pi by 8 plus 1/8 sine of pi. And sine of pi is 0. So we end up with just pi by 8 as our area measurement. Okay, so to find the area between two polar curves, you are going to do basically the same thing, but you would take the the top curve, the equation for that, square it, and subtract the bottom curve squared. Still need the 1/2 as part of your computation. You still have an interval that you are working with. Okay, now here's the catch. This really only works if there is clearly a curve on top and a curve on bottom. If there's like a side-to-side thing, you're not going to be able to use this technique. We will talk more about that next week. So here's a straightforward example. Find the area of the region that lies inside the circle, r equals 3 sine theta. And outside the cardioid, r equals 1 plus sine theta. So again, the picture is super helpful because it gives you those theta values where it begins and ends, but that may not be given every time. So in this particular question, what you would want to do if those values are not given is you would want to graph them and see what it looks like. And then to find the values, set the two equations equal, because this is clearly where they intersect, and that's what I want to find. So we are going to solve the equation. I can subtract a sine, and I can divide. So it becomes sine of theta equals 1/2. Basically, when is sine equal to 1/2? That occurs at pi by 6, 5 pi by 6, negative pi by 6. Things like that will work, and obviously that's what we're dealing with here. Okay, so to set this up, pi by 6 to 5 pi by 6. We have a 1/2 as part of our formula, and then top curve squared. So 3 sine theta is on the top of this diagram, so that goes first, minus 1 plus sine of theta squared d theta, okay? And then this just becomes like a really big algebra problem essentially, because there's not a whole lot of real difficult stuff happening. You are going to run into a situation again where you're going to need a trig identity, so just a heads up about that. I would square everything and combine like terms. I'm not going to show all of those steps. I do want to put the 1/2 out here. Let me put the 1/2 out there. I'm not going to show all those steps because I trust that you're able to FOIL and multiply and all that jazz. So I'm going to get straight to what it would look like once like terms are combined. It would be 8 sine squared theta minus 1 minus 2 sine of theta d theta. And we now need a trig identity because we have a sine squared. And so we can't integrate that. So what we're going to do is do another substitution deal. Again, this is a trig identity. It's either the half or the double angle formula. I can't recall right now, but you use this one a lot. So we're doing a substitution right here using that trig identity. I'm not integrating yet, by the way. I'm just trying to get it to the point where I can integrate it. So let's see here. I would have 8 times all this, which would just be like 4. So 4 minus 4 cos of 2 theta. I think if I, distribute and do all that stuff, minus 1 minus 2 sine theta. And maybe let's combine the 4 and the minus 1 right now before we integrate. So that would make it a positive 3. Okay, so integration time. I have, actually I think what I'm also going to do real quick, I'm going to change this interval to pi by 6 to pi by 2. This is another one where it's symmetric. This one is symmetric about the y-axis. So I think maybe I'm just dividing my area in half. And then I had a 1/2 out here. So I'll just double whatever this answer is, and that'll give me the same result. Okay, which now these are going to cancel. So it kind of works out really nicely. My antiderivative would be 3 theta minus 4 sine of 2 theta, but you have to divide that by 2 because of the baby, plus 2 cos theta. Evaluate that from pi by 6 to pi by 2. And you end up getting 3 times pi by 2. If I plug pi by 2 in here, it becomes pi, which that would be 0. Cos of pi by 2 is also 0, so that's gone. Then we go to minus 3 times pi by 6 plus 2 sine of 2 times pi by 6 is pi by 3 minus 2 cosine of pi by 6. Okay, I think I've got everything there. Solve all this out and you should end up just being pi in the end. All right, so last example, find the area of the region inside the circle r equals 4. That is the red circle on this picture. And outside r equals 4 minus cos theta. Okay, so first we need to find where they intersect. So we're going to set these two equations equal to one another. Solve, and you're going to get theta is equal to pi by 2 and 3 pi by 2. Now, it would be super helpful to watch these things be graphed. So this is pi by 2, this is 3 pi by 2. Now, watch it graph and pay attention to the angle measurements. Also, remember, this could keep going. We could have negative pi by 2 and so on. So how do you know which one to use? Well, we want it to be inside the circle and outside of the the 4 minus cos theta. So that would be like this area here, okay? So if I were to analyze the graph from pi by 2 to 3 pi by 2, pi by 2 to 3 pi by 2 would be this wedge, okay? This wedge actually visually looks to me like it might be a little bit different in size. So I need to kind of go over here. I don't want to assume that these are symmetric. So I'm going to go over here, and that means I'm going to have to adjust my angles. I'm not going to be able to go from pi by 2 to 3 pi by 2. I need to start down here and go up this way. So that means I'm going to use negative pi by 2 to pi by 2 as my interval. And again, that's something that you would just want to play around with when you are using your graphing calculator. It's going to make it a lot easier if you watch the graph kind of come into kind of be graphed and created. Watch the way it turns, play around with the theta values until you find what's going to work in that particular situation. Okay, so if I look at just this wedge individually, I would agree that it's symmetric. The x-axis divides it in half exactly. So I am going to do the adjustment with the interval and make it 0 to pi by 2. And that means that the 1/2 would cancel with the doubling portion that would be on the outside. The other thing that I'm going to do is I'm going to simplify all this, which I would have a 16 minus 16, so that's going to cancel. And if I, go ahead and multiply everything out and combine like terms and all that, I would end up with 8 cos theta minus cosine squared theta. And so yet again, we're in a situation where we need to do a trig identity. So cosine squared of theta is equal to 1/2 times 1 plus cos of 2 theta. So we're going to make that substitution here so that it is something that we can integrate. So as you can see, these problems are kind of repeating themselves in that they have similar steps each time. Okay, I think once I get to this point, I'm ready to start integrating. So the antiderivative would be 8 sine theta minus 1/2 theta minus, this would be 1/4 because you have to divide by baby, 1/4 sine of 2 theta. Evaluate all that. I'm not going to show all my work because I feel like you are capable of that at this point, but the answer would be 8 minus pi by 4 for the area measurement.